and thanks to everybody for coming. So today I'm going to be talking about post-quantum succinct arguments, which is a paper with my former advisor, Alessandro Chiesa, Femi Ma at Princeton, and Mark Gentry, who's also at Princeton. And thanks to Femi Ma for some of these slides. So let's start off with maybe something that we're not all familiar with. What is a succinct argument? So a succinct argument is a type of proof system for NP. You have an NP instance X and a witness W, and you have a prover who is trying to prove to a verifier that the instance X is in this NP language, and the properties that you want from the system are sort of the standard ones, and then one sort of extra thing. So firstly, the completeness says that if X and W are in R, then if you sort of run the honest prover, then the verifier will accept. Soundness says that if X is not in R, then no matter what you do, what the malicious prover does, the verifier should always reject with high probability. And so far, if you just have completeness and soundness, then you could just, send the witness, and this would be a perfectly good fulfillment of this definition. And so we also require, in order to make this non-trivial, a succinctness property, which is that the communication should be polylogarithmic in the size of the instance and witness, and polynomial in potentially in some security parameter to lambda, which sort of determines the probability that the verifier will accept if the instance is not in the language. You can sort of ignore this lambda if you want to. So one thing that's important is that soundness can only hold against malicious, efficient adversaries, and this is because of some complexity theoretic reasons. Basically, you need to make this relaxation. This is different to sort of interactive proofs, which involve soundness against like even unbounded adversaries. So here we're making some computational assumption about the power of our adversary. Okay, so how do we build these things? Classically, there is a fairly simple construction due to Killian from collision-resistant hash functions. And I'll show that in a second. The question that sort of naturally follows from that is, do post-quantum succinct arguments exist under standard post-quantum assumptions? So, we have the simple construction classically, like what can we do in the quantum setting? And in this work, we show that post-quantum succinct arguments exist given the quantum hardness of learning with errors, post-quantum hardness of learning with errors. And this is the first construction of post-quantum succinct arguments from any standard assumption or even any falsifiable assumption. I wouldn't say what that means, but for people who know what that is, this is sort of a class of assumptions that includes any standard assumption. There were some prior positive results, which I just mentioned. So you can get succinct non-interactive arguments in the quantum random oracle model, or using some kind of post-quantum lattice-based knowledge assumption. But these are not falsifiable assumptions. So, okay. So an actual question is, we have succinct arguments from collision-resistant hash functions due to this classical construction of Killian. Why doesn't this immediately give us post-quantum succinct arguments if we just like make the CRHF post-quantum? Right? I mean, we believe that there exists post-quantum CRHF, so why not just do that? And the answer is that the answer is in a word, rewinding. So I'll show a little bit about what rewinding is in just a second, but basically rewinding is an important component in the security proof of Killian, and quantum rewinding is hard, according to this paper. So what is Killian's protocol? What it does is it takes a probability checkable proof and compiles it into a succinct interactive argument using some cryptography. So a PCP is a proof system where you have a verifier that checks an MP statement by, rather than sort of reading the entire witnesses in a usual MP proof system, it chooses some random positions in this string and it queries them. And it has been shown that you can build PCPs where the verifier only needs to look at a small number of positions in the proof, in particular some sort of polylogarithmic in the original witness size. Okay, so how does Killian's protocol work? The prover is going to send a commitment to the PCP that he's generated from the witness. This can be generated efficiently. Then the verifier will choose a collision resistant hash function, and the prover will compute what's called a Merkle tree, sort of on top of this proof. So a Merkle tree is a way of committing to a long string such that you can open individual positions in an efficient way, basically by computing a tree of hashes on top of the string. Acting as the PCP verifier, the argument verifier is going to send a query set Q. So these are the queries that he's interested in making to the PCP string. And he's going to ask for the positions of the PCP at this query set. The prover is going to send those positions along with information that allows the verifier to check that these positions these values were indeed the ones committed to at these positions. So these are called opening proofs. And then the verifier will accept if the openings are valid, and the PCP verifier accepts given pi q. Okay, so that was Killian's protocol. Are there any questions about that? I guess maybe it's like if you've not seen it before, or you're not familiar with PCPs or Merkle trees or something, then it might be
something, Nick. Hi.
Sorry, yeah.
Is there a way to make this non-interactive using some sort of Fiat-Shamir transformation?
Yes. So this is actually how the construction in the quantum random Markle model previously worked. So you can use Fiat-Shamir. You can so long as this Q here basically random bits, then you can use Fiat-Shamir to squash this to non-interactive. And actually, soundness of this was already known prior to this work. So this sort of is a little bit backwards. Yeah, you can prove the Fiat-Shamiring is sound, but it's harder to prove that the interactive protocol is sound.
Thanks.
No problem. Okay, so how do we prove security in the classical setting for this protocol? So what you do is you run so you have this adversary, and you run the adversary by sending him a random CRHF, and he gives you back a commitment to the proof string that he's committing to, and then he has some intermediate state S that you save, and then what you do is you ask a query. You ask the adversary a question, and then the adversary will give you an opening and the positions that it claims, and you do this over and over again. So you take the state S, the intermediate state of the adversary, and you make a bunch of copies of it, and then you ask each of the copies for a different query set. And if you do this enough times on a bunch of different query sets, then eventually you will attain enough information to reconstruct the PCP. And eventually what happens is that if the adversary success probability is too high, then one of two things is going to happen. Either you're going to find a collision in the hash function, so you're going to break this Merkle tree commitment, or you're going to find a proof, like a PCP pi that has too good a success probability, and these can't exist because of the soundness property of the PCP. So that's sort of the full classical proof of security. Any questions about that? Okay, so to sort of see where things go wrong in the quantum setting, I'm going to abstract away this Killian protocol. So for the rest of the talk, I'm actually almost not going to talk about Killian. So if there's anything confusing about Killian, please ask now, because I won't really come back to it. Okay. So the abstract problem that you have to solve in order to do the security reduction for Killian is called the rewinding problem. So you're given some algorithm that has an initial state, and you can query it with random strings, so with some input, and it gives you back some output. And you have the property that for this verification algorithm V, if you query it the adversary with a random string and you get back an answer Z, then the probability that the verifier accepts that answer is epsilon. That's the guarantee. And what you want to do is, given that epsilon is sort of quite a bit bigger than k over the size of R, which is the set of random strings that you can give to the adversary, you want to obtain k distinct, k transcripts, so like k pairs Ri Zi, such that V of Ri Zi is equal to 1 for all I, and the Ri are distinct. Okay, so this is the rewinding problem. And if you can do this, then basically you can prove that Killian is secure, and a number of other protocols too. So classically, the rewinding problem is easy. So what you do is you just, like I said, you make a bunch of copies, and then you try a random R until you get k accepting transcripts with distinct R, and this happens sort of after roughly k over epsilon trials, right? So you sort of, provided R is reasonably large, you can just run it k over epsilon times, and you'll see successes for distinct R's. Okay. So what does this look like? This is the picture, right? So you just make a bunch of copies of the adversary, and you run it a bunch of times, and the probability that any of these succeeds is epsilon. And these are independent for all instances, because you just made independent copies. Okay, so what happens when A is a quantum algorithm? So now A may have as input a quantum state, and this epsilon is defined in the same way. It's just the probability that over R that A outputs something that causes you to accept. So two problems happen, two things occur, I guess. Firstly, because of no cloning, you can't make copies of rho. And so this means that you sort of are restricted to, like, you only have one copy of rho, you're sort of restricted to performing the trials one after the other in some way. And moreover, the state is going to be disturbed by the action of producing this classical Z, right? So the adversary is going to make a measurement to, at the very least, produce this response Z, and this is going to cause the state to be disturbed. Okay, so these are the two problems. And so what this means is that rewinding for a quantum adversary looks more like this, or the rewinding problem looks more like this. So you need to, you run a trial, you sort of choose a random R1, you get a result Z1, but then you have to sort of use the residual state that you get after you run the adversary to run him a second time. So then, obviously these trials are not independent because the state is carried between them. So the question is, if we look at the success probability of each trial, epsilon I, what can we say about epsilon I in terms of epsilon 1? So in order to talk about this, I'm going to have to introduce a little bit more cryptography. There is a notion which is called collapsing, which is the cryptographic notion, and what it says is the following. So let's imagine an experiment where we have some adversary that is taking in this row and taking in the randomness, and he is, rather than outputting a classical Z, he's going to output, we think of him as being unitary, and so he's going to output sort of a superposition, like a coherent superposition of z's. Right? So this is sort of the same as the previous adversary, but now we just don't measure the output z. Right? So A here is unitary. Then what we do is we coherently apply the verifier of the protocol, this V algorithm, and he outputs a bit B, which says whether he accepts the response or not. Okay? So this is all happening coherently, apart from this bit B, which is a measurement. It's a measurement of whether the thing was successful. Conditioned on this outcome, so if the bit B is 1, if the verifier is accepting, then we measure the Z register. Right? So the verifier checks checks sort of coherently whether the Z register contains an accepting response. If it does contain an accepting response, then we measure. So this is the experiment, and if it does not contain an accepting response, then we don't do anything. So this is sort of what this little arrow from V to the measurement is. And I'm going to call this the state after this experiment rho 1. Sorry.
So the bit B is measured, or is it like is the output of the verifier in a coherent superposition as well?
The bit B is measured.
Okay.
Yep. So the verifier is like this V is a binary projective measurement. Okay. Now let's think of a different experiment where we do the same thing, except that we never measure anything. So we never measure, do this like second measurement of Z. So what we're going to do is we're going to just measure the bit B, which is does the verifier accept? This is just a single bit, and then otherwise we do nothing. Right. So this is like basically like we just remove the measurement of Z from the other experiment. And what collapsing says is that, so it's a property of this verify algorithm V. And it says that for all efficiently generated states rho and efficient adversaries A, which are, so this is QPT, right? The states rho 1 and rho 2 are computationally indistinguishable from each other. So there is, like, for every QPT algorithm, no QPT distinguisher can tell the difference between the state rho 1 and the state rho 2. So I guess what this means is sort of that this measurement of Z is kind of computationally invisible, right? Like you can't tell you can't tell computationally that I did it, given that I did this measurement, like the V measurement. So we can show that Killian's protocol is collapsing, provided you choose your CHF appropriately. Like it has to be a sort of what's called a collapsing hash function. And what this means is that for the rest of the talk, I'm going to consider A to be a binary projective measurement, which rather than producing the response Z, produces only a bit B that says whether the response Z is accepting or not. And this is okay because from the perspective of the extractor algorithm, like he can't distinguish between these two worlds. And this means that sort of anything that holds for binary measurements is also going to hold for this other world where you fully measure this register Z. Okay. Are there any questions about that?
Yeah, sorry, quick question. Sort of traditionally, if these are all sort of classical experiments, you might be able to stack, polynomially many of them in sequence and then just make sort of a hybrid argument that you could, do 100 of these and you would still not be indistinguishable at the very end.
Yeah.
Is that still going to hold in sort of a quantum setting where you might have sort of some superposition of attacks over these 100 steps and then make the argument that you're still polynomially close to between the first and the last one?
Yeah, so I mean, you have to be a bit more careful, but there is, you can do a hybrid argument also in the quantum setting, right? So you just, I mean, if you think about how the hybrid argument works, right, you just, from the difference between two hybrids, you need to be able to break the assumption. And so you need to make sure that still works, when everything is quantum, but you can do such a thing. And actually, this is sort of we will use this property many, many times, and so we do need to do a hybrid argument. Yeah.
Okay, cool. We can see. Thanks.
Okay. All right. So now we're going to be in a setting where where we have A that outputs a single bit, right? So I've replaced these Zs with bits B that just say whether or not the verifier has accepted the would accept the answer that is on the Z register. Okay. So this means that this probability now just becomes like this probability epsilon I, it becomes the probability that BI is equal to 1. And we want to lower bound this probability. There is some prior work that does give you some lower bounds on this probability. So this is Unruh and some of the people on this call, I believe. I think it was Don, Fair, Mayans, and Schaffner. Oh, there you go. What they show is that if you take the product of the first k epsilons, then this is at least epsilon to the 2k minus 1. So this, the product of the first sort of k success probabilities is at least epsilon to the 2k minus 1. And so for constant k, this is fine actually, because if epsilon was sort of inverse polynomial, then each of the epsilon i's will also be inverse polynomial, or this product will also be inverse polynomial. And so you can actually use this to do useful rewinding if you only want constantly many rewinds. For succinct arguments, this isn't enough, because in order to obtain succinctness, you need to do super constantly many rewinds. This will cause your epsilon, like this guarantee, will no longer give you anything useful. One thing to note is that even classically, the probability that like all the first case trials succeed is epsilon to the k. So this actually, this is what the bounding rewinding lemma is saying, is that quantumly the probability that all the first k trials succeed is epsilon to the 2k minus 1, and actually classically this is like very similar. But what you do in classically is you just run it many more than k times, and then with very good probability at least k of them will have succeeded. The problem in the quantum setting actually is that if you do this and you're not careful, then the epsilon i's can actually decay exponentially fast. And we show in the paper that there's a situation where the expected number of successes over all time, even if you ran forever, would be about 1. So this is sort of this is where you get stuck. So the problem that we have, right, is that this epsilon value may drop after each trial, right? So like we want to see a large number of successes, but the problem is that the probability of success may be damaged by applying the algorithm A. And so what we do in the paper is to build a quantum procedure which repairs the success probability to approximately epsilon after each trial. So it sort of it takes a state with a damaged success probability and it repairs it to a state which has a almost as good success probability as the original state. And this now means that once you have this procedure, you can run as many trials as you want, because the success probability only goes down a little bit. And so if you make that little bit small enough, then you can run as many trials as you like. And this is how we complete the proof. Okay, so for the rest of the talk, I'm going to explain how this repair procedure works. But so for now, I want to ask, is it clear like why this repair procedure solves the problem?
So do you need any property from row I+1 and row star I+1, or like?
So the only thing that we care about is that it, that it causes the adversary to produce an accepting response with high enough probability.
So we don't need them to be indistinguishable or these kind of things.
No, nothing like that. Yeah, actually, so the repair procedure is sort of not like it really only like the only guarantee that we can really give is that it fixes the success probability. Actually, like rho I and rho I plus 1 star like might be very far apart, like very distinguishable.
Sorry, there's still some property that I'm missing because this repair could just replace rho I plus 1 by rho I, right? So
could replace it by rho I.
Like for a fixed row, for example, that's the input, or
sure, yeah, but you don't have access to another copy of rho I. So
okay.
Yeah. So the rho I is really like you have one copy of it and you need to take very good care of it. Yeah.
Okay.
This arises because basically the rho I is going to be the state that appears in the middle of the execution of the protocol, and so in general, like it's some intermediate state of some computation, and which involved a measurement to produce the Merkle root, and so this means that it's like not you can't produce another copy of it.
So sort of going back to the beginning, it doesn't matter if your successful instances look very weird, look like they came from distributions that are really sort of arbitrary or unusual or distinct. The important point is just to mine the world for a bunch of them, and then once you have a bunch of them in hand, then you're good. It goes back to that goal. Okay.
Precisely, yeah. Yeah, so that's all. Like you just need to produce. Like in order to prove security, you just need to produce successful transcripts for different choices of RI. And once you have enough, then you win. So that's really all we're going to try to do.
Are you going to exploit that these BIs are bits?
Yeah, that's important.
Because otherwise, yeah.
Yeah. Otherwise, basically, like if A had too many outcomes, right, then rho I plus 1 could potentially like lose all of the information from rho I, and then you would be, yeah, this would be no good. Yeah. Okay. So in the rest of the talk, I'm going to explain how this state repair procedure works. So here is like the one slide summary. Let's imagine for a moment, this is false, but imagine that there is this linear space, like a subspace, that contains all of the sort of states that have success probability at least epsilon. Here I'm moving to pure states, but everything sort of works by convexity, right? Then the initial state having success probability at least epsilon is going to be inside of the subspace by definition. Moreover, because the measurement is only a 1-bit measurement, it doesn't disturb the state too much when you apply it, and so the sort of post-measurement state is not too far from the original state that you were at, right? Because you made a 1-bit measurement. And then what you do is you somehow push the state back into the good subspace using this alternating projections algorithm, which I'll talk about in a second. So that's sort of the basic schematic. So there are a couple of problems with this outline. Firstly, I lied about the set of good states being a linear space. However, there does exist a linear space such that everything in the space is good, and also if you are a good state, then you have a pretty good overlap with the space. So this is sort of good enough. And the second problem is that in order to sort of use alternating projections to push the state back into S, you need to have an efficient projection onto S, or potentially a rotation onto S. But we don't have such a thing. At least we don't know how to implement such a thing. And so we need to come up with sort of a specialized variant of this procedure, which works with an approximate projection for a sort of reasonable notion of approximate projection. Okay, so that's going to be the schematic, and now I'm going to fill in the details. This problem 2 is most of the technical work in the paper. So to start with, let's talk about a simpler problem, which is probability estimation. So rather than repair, you just want to figure out what is the probability that the adversary will produce the bit 1 on a state psi using only one copy of psi. So if you have many copies, you can just, you can do sort of the classical style thing. You can just run the adversary many times. Here, you just want to use only one copy. And so some of you may be familiar with this algorithm due to Marriott-Watrous, which achieves this. So what you do is you run a controlled application of A, where the control bit is going to be the plus state. It's going to be in the plus state. So if you trace out the first register, the plus state register, then it looks like a random choice of R, and so this bit B1 is going to be 1 with probability P. But then what you do is you project the first register back into the plus state. So you apply the projection onto the plus state, and it will either succeed or fail. If it succeeds, then the first register is going to be back in the plus state. And then you keep going. So you just do this for some number of trials, and the number of trials that you do gives you, the more trials you do, the better the guarantee is on the estimate that you got. And what you output is the number of I such that BI is equal to BI plus 1 divided by the number of trials. So you look at like adjacent bits, and if they're the same, then you score 1, and if they're different, you score 0. You add up your score, and then you divide it by the number of trials. And what was shown in Marriott-Watrous and later also in our work and in Mark Jandry's trace tracing paper is that the expected is that this p tilde is an unbiased estimator of the success probability. So the expected value of p tilde is the probability that A outputs 1 on a random R.
Sorry, can I ask a question?
Yeah.
What do you do if a measurement yields cat minus instead of cat plus?
So sorry, you mean the like if this measurement on the plus this pi plus yields a 0 outcome?
Yeah, so I guess the two, there's 2 possible measurement outcomes, right? You would like to see one, but what do you do if you get the other measurement outcome?
You keep going. So it's sort of easy to see what happens when you get a 1 outcome on this plus measurement. If you get a 0 outcome, it's sort of less easy to see, but it works out. You count that as a 0.
Okay, thanks.
So I'm gonna attempt to sort of show the analysis of this algorithm. I think it's very, very cute, and I guess kind of deep. So the tool that you use is Jordan's lemma. So if you have 2 projectors, then these projectors jointly decompose the Hilbert space into subspaces of at most 2 dimensions. And for this talk, I'm just going to think about all the subspaces as being 2-dimensional. 1-dimensional subspaces are sort of uninteresting. And the 2-dimensional subspaces look like this. So on each 2-dimensional subspace, both pi1 and pi2 act as rank 1 projectors. So pi1 on the jth subspace projects onto the vector vj, and pi2 on the jth subspace projects onto the vector wj. And the subspaces themselves are all orthogonal to each other. So what this looks like is that inside of the subspace Sj, you have 2 sort of orthogonal spanning vectors, vector pairs, which correspond to the pi1 and pi2 axes. And there is a very important quantity related to the subspace, which is the angle between pi1 and pi2, or the projection of Vj onto Wj. This is the angle is often called the principal angle. What we call this this Pj value the eigenvalue of Sj, because it's an eigenvalue of this Hermitian matrix pi1, pi2, pi1, and also pi2, pi1, pi2. But this is a very crucial quantity in the analysis of these alternating projectile algorithms. Okay, so this was Jordan's lemma. And what it allows you to do basically is to take any algorithm that consists of alternating two projectors, such as the one that I just described, and analyze it in terms of two-dimensional subspaces, like in terms of qubit dynamics, which makes things quite a bit more straightforward. So let's look at this in terms of Jordan's lemma. So I can write the projection onto plus. So that I've omitted here a tensor with the identity on the other registers. I can write this as a sum of rank 1 projectors onto these VJs, and the controlled application of A as a sum of rank 1 projectors onto WJs. And let's suppose that my initial state in the estimation algorithm actually lies completely within one of these subspaces Sj. This means in particular that it is equal to some Vj, because plus psi is for any psi is a +1 eigenstate of pi plus. So this is going to be equal to some Vj if it lies completely in Sj. So let's recall that Pj, the corresponding eigenvalue, is equal to the norm of the inner product between Vj and Wj, which is equal to this Vj Wj Wj Vj thing, which is actually equal to P. So it's equal to the norm of the controlled application of A to plus psi, which is P. So at least for eigenstates, it's this Pj is the thing that we care about. And so what happens during the procedure? Well, you start out in the state Vj, and then you apply the Ca. And when you apply Ca, what happens is that you end up in you end up with the state square root Pj Wj, which if you normalize it, it's just Wj. And this happens with probability Pj. And if you get a zero outcome for Ca, then you end up in this Wj perp state, and this happens with probability 1 minus Pj, so symmetrically. And so we now know, like, there are two possible states that you could be in after the application of C sub A. So now what happens if you apply this plus measurement? Well, if you're in this Wj, then sort of by a symmetric argument, you can see that you sort of move to the state Vj with probability Pj, and you move to the state Vj perp with probability 1 minus Pj. And you can also show, I'm not going to sort of go through it, but you can also show that if you're in Wj perp, then you move to the state Vj with probability 1 minus Pj, and you move to the state Vj perp with probability Pj. So what's happening, right, is that you stay in the one sort of in the one outcome state with probability Pj, and you flip to the zero outcome state with probability 1 minus Pj every time. And this this continues to happen. So this is sort of the dynamics of the entire system. And this means that this P tilde is distributed as a binomial random variable with for n trials with parameter P sub j divided by n. So at least for the case of sort of when you're in an eigenstate, this is an estimator of P sub j. Okay. Any questions about that? I'm going to do the general case. Okay. So in the general case, what we do is we decompose this state as a sum of these Vj vectors, right? And so now P is going to be the weighted sum of the Pj's according to the amplitudes of the individual vectors. And for the analysis, what we're going to do is we're going to define this Jordan measurement, which projects onto the sort of individual subspaces Sj. This is a very useful tool for analyzing these procedures. And one thing to note is that Mj commutes with both pi plus and Ca, because if you look at each of these elements, they're diagonal in both the Vj and Wj bases. So this measurement commutes with every measurement that we make during the procedure, which means that if you make the measurement at the end, then obviously it can't affect the distribution of outcomes, and so because it commutes with everything, we can commute it to the beginning of the procedure, where it still does not affect the distribution of outcomes. And after we make this measurement, then we're in the state Vj, if we get an outcome J for this measurement. And then we can apply the previous analysis. So what this means is that this P tilde is a weighted sum of these binomials, right? So if I get the outcome J from Mj, then I'm in the sort of I'm in this Vj case, and the probability that I get the outcome J from Mj is alpha J squared. So this is so the distribution of this thing is a weighted sum of binomials weighted by the coefficients and with parameters that are the eigenvalues, corresponding eigenvalues. And if you take the expectation of this expression, you get sum of alpha j squared pj, which is p. Okay, any questions about this, how this works? So this is all credit to Marriott and Watrous. None of this is our work. Okay. So now that we've done this analysis, I want to kind of take a step back and think about what is happening to the state during this algorithm. So I'm going to define this di to be equal to like whether bi and bi plus 1 are equal. So it's 1 if they're the same and 0 if they're different. And what the analysis actually tells you is that d1 up to dn, if you sort of run this for n plus 1 steps and you compute d1 up to dn, is distributed as a weighted sum of the product of n independent Bernoullis with parameter pj. So what does this mean? So now I'm going to think about running it for 2 n steps rather than n steps. All right, I just changed the n to 2n. What this means is that you can model this as I choose a parameter p to be equal to pj with probability size of alpha j squared, and then I sample each di from Bernoulli distribution with parameter p. In particular, all of the di's are correlated with each other. So let's think about now dividing this procedure into 2 halves, right? We divide it into like d1 up to dn and dn plus 1 up to d2n. By a Chernoff bound, this h is the Hamming weight of this string, so it's the number of ones in this string. By a Chernoff bound, the number of ones in the first n and the number of ones in the second n, because it's a Bernoulli with the same parameter, must be very close together. And sort of the difference between them is at most sort of some square root n with extremely high probability. But if we think about the procedure, the second half of the procedure is just, it looks like an independent copy of the procedure just applied to the state that sort of results from the first half of the procedure. And so we can actually use the analysis of the procedure right here. And what this shows is that the state is now, like in the middle of the procedure, is now concentrated on, sorry, this should be a VJ, not a psi j. So it's concentrated on VJ such that PJ is close to the estimate that we got in the first half of the procedure. Right, so this P tilde is the estimate that you get in the first half. When you get to the middle, because of this sort of probability expression, it must be the case that the state psi prime is concentrated on these VJ eigenstates, or possibly VJ perp eigenstates, depending on whether the pi plus measurement gave you a 0 or 1. But in any case, it's concentrated in subspaces such that the eigenvalue of the subspace is close to this P tilde. Does that make sense why that's the case?
Can I ask a question? Like, so these D1 to Dn, are they, did you say they are independent?
They are independent up to, so they're like a convex combination of, like a linear combination of independent, like Bernoulli trials. So you choose, like the way that you can sample them is you choose the parameter according to the distribution, and then you sample them all independently from like independently as Bernoulli's with this parameter. So they're correlated in the sense that the parameter is the same. Right, they're correlated in this particular way, but otherwise they're independent.
I think I don't quite understand the notation. So like this D, in your yellow box, this D1 Dn, is this a multiplication of this?
Sorry, no, this is a string. Yeah.
So it's just all.
It's like the bit string D1 up to Dn is distributed as like this linear combination of the sort of this like n-fold product of Bernoulli random variables.
But if you say n-fold product, then they are independent.
So the individual components of the combination are independent.
Okay, and then you take a kind of
a
combination of those.
Yeah, exactly. So they're independent conditioned on the choice of J, basically. Yes.
Okay, now I understand. Maybe can you now repeat the argument you made at the end? Because I think.
Sure. Yeah. So in particular, right, this like conditioned on this choice of J, that you get like you get a bunch of Bernoulli trials, and Chernoff bounds tell you that the sort of the value in the first n trials is concentrated around its mean, and the value in the second n trials is concentrated around its mean. In particular, these are both concentrated around this P that you chose in step 1. But what you can infer from this is that it must be that the state in the middle is also concentrated around this P. In particular, it's concentrated around the P tilde that you measured in the first half. Because this distribution is now behaving as though you already sort of picked P. Like you picked this J.
Yeah, you pick the J kind of at the beginning, and then you will still have the same J in the middle of this procedure.
Yes, exactly. And so this means it must be the case that the state has changed in order to cause this to happen.
So that's actually sort of hitting on the maybe trivial clarifying question that I have, which is that, is it the same as picking a single J here, or the distinction between these psi J's, maybe they have the same P tilde values. Yeah. Like if you had 5 of them, are you into some 5-dimensional subspace? Is this amplitude focused on a subspace, like multiple one eigenvalue having multiple eigenvectors. I'm
right, yeah. So actually, yeah. So it's not the case that it's concentrated on sort of a single two-dimensional subspace, but you will get a concentration on eigenspaces on subspaces that have value that is close to this p tilde.
Okay.
Yeah.
So sort of a spectral analysis, you get close to this eigenvalue, and then it's a subspace. That's
exactly. It's like there's some sort of I don't know if I can draw on this. I guess I can't. There's some sort of bell curve of concentration which is centered around this p tilde that you measured in the first half.
Okay, thanks.
Okay. So what does this mean? Well, this means that the estimation procedure is already sort of a repair procedure. Because suppose that the estimation procedure outputs a p tilde which is close to the original close to the original success probability. Let's just imagine like this is I'm not saying that this will happen, but like let's suppose that it does. Then the amplitude is actually concentrated around p tilde, which means that the resulting state has success probability roughly p tilde, which we said is around the probability that the original thing accepted. So in the case that the estimation algorithm outputs this p tilde that is large enough, actually the state is repaired. And the probability that happens is actually not too small, basically because this A measurement was did not disturb the state very much. Like it's a binary measurement, so the estimation procedure should give you p tilde that's close to p with good probability by its own guarantee. And if I apply a measurement, then this can't change by very much. The probability that if I apply a binary measurement, the probability that this happens can't change by very much. Still, it's going to be smaller, and we want it to happen. We want this to actually happen with probability close to 1. Like we can't afford to lose at every step, and so there's still more to do, because basically what we want to do is we want to kind of force the estimation procedure to output a p tilde which is large enough. So how do we do that? The first thing that we do is we turn the estimation procedure into a projective measurement. So this is the sort of projective version of this estimation procedure. We have some ancillary registers, and we apply the A and pi plus measurements coherently. Then we compute whether the estimate is high enough for our purposes, whether it's at least epsilon. And then we uncompute everything, right? So this turns this estimation procedure into some projective operation, which we're going to call pi sub e. So that's the first step. It's sort of a standard thing to do. Now the state repair algorithm works in the following way. So let's look at what happens when we apply. So we have our state psi. We apply this algorithm A. This is like the test, and now we're going to look at the state repair. So it looks like this. So it's an alternation between. So the only algorithm that I know is alternating projectors. So it's an alternation between this pi sub e and another projector measurement pi sub b. And what is this pi sub b? It is if b is b is the outcome of the original trial, right? Of sort of the test part of this test and the repair procedure. And if b is 1, then you apply a of r on the psi register, and then you project the ancillary register back onto 0. So this is a 1-bit measurement that is the AND of these two conditions. And if b is equal to 0, then you're still projecting the ancilla register onto 0, but you apply I minus a of r to the psi register. So you kind of flip the sign of the a projection, and you do take the and of these. And you repeat this until you get 2 successes in a row for an even number and then the subsequent odd number, right? So so if you get successes so we'll take b0 to be equal to 1. If you get a success in the first, for pi sub e the first time, then you accept. And otherwise later on, let's say you get a success for b4, then b5, then you're done. Okay. So firstly, why do you want to project the ancilla at all? The answer is that this pi sub e is only going to actually do anything useful when the ancilla is in the state 0 to the n. So, you know, in general, the ancilla is going to be in some other state, and you need to fix it. So, then why does this work when the procedure terminates? Well, if you see one outcome for pi sub b, this means that the ancilla is in the state 0 to the n, right? If you then see a one outcome for pi sub e, this means that the state repair procedure has succeeded, which means that it succeeded in like output something that is large enough, and therefore the state is repaired with high probability. Okay. So the question is, you know, why does it terminate? Like that's sort of the key thing. So does it make sense? Like why, if this procedure terminates, then we're good. Like we've repaired the state. By the way, I know I'm slightly over time, but so let me know if I need to stop. I only have a couple more slides. Okay.
It's fine. I mean, we started a bit late.
Okay, great. Then I will finish it off. So okay, so why does the procedure terminate? So firstly, note that the way that we've defined pi sub b, we can replace this measurement A that produces an outcome B with, you know, we can sort of as a thought experiment replace it with this measurement pi sub B, which is going to always output 1, right? So like we can sort of like rewrite history and imagine that we made the measurement pi sub B and an output 1. Okay, so now this thing might look very familiar. This is once again alternating projectors, and so we're going to analyze it in the same way as we did the probability estimation procedure. So let's say that pi sub e is sorry, there should be a sum here. The sum over j of vj of the projection of the vj's, and the pi sub b is the sum over j of projection of the wj's. And let's suppose also let's assume that the initial state is actually in the image of this of pi sub e. So this I realize this might be covered by my face in the video, but anyway. So let's assume that the initial state is in the image of pi sub e. This is something that you can approximately guarantee, and I won't go into how, but you can do it. So this means that you know, if you focus on a single subspace, then we start in the state v sub j for some j, and we know that we know because of the way we defined everything that pi sub b has a 1 outcome, right? Like the application of this pi sub b measurement has a 1 outcome, which means we move from vj to wj. And because this happened, we know actually that p sub j cannot be too small. Otherwise, this would not have happened. Okay. So now we apply pi sub e again. And in the case where we get a 1 outcome for pi sub e, then we're done, because we've had these like 2 consecutive 1 outcomes. Okay. If not, then this means that we've actually sort of transitioned to the 0 part of this diagram. And in particular, this does not happen if 1 minus pj is really small. So if 1 minus pj is really small, then with extremely high, with very high probability, you sort of need to balance these things out, but with very high probability, you are going to stay on the top of the diagram and you're going to stop immediately. If neither of these things are really small, right, if pj and 1 minus pj are sort of both not too small, then if you keep applying this, if you keep applying these alternating projectors, then you're going to bounce around between 1, 0, and 1 sort of randomly, right? Like if the transition probability is not too small, then you're going to sort of jump up and down. Like it's a sort of this sort of mixes, right? And because it mixes, the probability of getting 2 1s in a row is like not that small, right? Because you sort of have enough entropy that this is going to happen at some point. And then as before, you can actually decompose this into, you can use this Jordan measurement to decompose the behavior of a general state into behaviors for eigenstates, for these VJ eigenstates. And what the proof shows is that the probability that you terminate, the probability that you require more than t steps to terminate in this procedure is something like 1 over square root t. So if you set this, this means that sort of this terminates in polynomially many steps with all but inverse polynomial probability, where you can set this threshold to be as large as you want. Okay. So what have we done? So firstly, I argued that proving security for succinct arguments requires a super constant rewinding. So you need to be able to rewind more than constantly many times. Quantum rewinding is hard because of state disturbance. In particular, the more you rewind, the more your state is disturbed. And so super constant rewinding is difficult. By collapsing, it suffices to restore the success probability of the state after applying a 1-bit measurement. So this was this argument that the measurement you actually want to make is indistinguishable from a 1-bit measurement, so you can just think about 1-bit measurements. And finally, we design a state repair procedure that achieves this guarantee. Thank you very much.